Alright, so the problem today is going to be find duplicate number. You're going to be given a list of integer nums, and the nums are going to contain n plus 1 integers. Each integer in nums is in the range of 1 to n inclusive. So our range of values is between 1 and n, but the size of our array is more than n. So in this case, n would be 4, but the size of the array here would be 5, right? And each element falls under this range. And then the next condition is there's exactly one repeated integer in nums, and every other integer appears at most once. So in this case, our repeated integer is 3. And of course, we can have more than one duplicate. In this case, we have 2 extra 3s here. This is also valid. But let's say if our input were to be like this, we have 2 3s and 2 4s. This wouldn't be a valid input because we have 2 sets of numbers that are duplicates. Oh, so only one number gets to be the duplicate. The easiest and most intuitive solution is to just loop through this list with a hash map. And then we'll collect all the elements that we've seen and we put it into a set. And if we happen to encounter an element that we've already seen, then that means it's a duplicate element and then we can return that. But they want us to solve the problem in just O1 space, and we're not allowed to modify the array. The solution to doing this in O1 time is frankly really unintuitive, but we'll try it anyways. Alright, so before I even tackle the problem, I need to tell you that this is going to be a linked list problem. And as a basis for this question, we need to talk about the anatomy of a linked list. Well, it's pretty straightforward, right? You have a head node, which points to an optional number of nodes in the middle. And in the end, we have the final node that points to a null, right? This would be an example of a non-cyclical linked list. However, if we're talking about a cyclical linked list, then our element in the end would be pointing to a previous element. For example, something like this. Technically, you can have elements in the middle that point to a previous number. For example, this 2 could point to a 1, like so, but then that basically just makes 2 the final element, doesn't it? But yes, final element needs to point to a previous number. So in effect, we kind of have 2 parts here. We have the head, which no node is pointing to. I'm going to call it the onset because this is going to be the onset to the cycle. Right? So for this one, I'm going to call it the cycle. And the onset is basically just the nodes that lead up to this node here, which is going to be the cycle start. Because if we're moving a pointer down this list, the moment we reach this element, we are now trapped inside a cycle, and then we're going to go round and round and round and round. Now, the reason I'm talking about this is because our input array, say it's 3, 1, 3, 4, 2, can be represented as a linked list. How are we going to do that? So as we know, in arrays, we have the indices, 0, 1, 2, 3, 4, and we also have the elements themselves, right? Which are these ones. And another thing is, conveniently, the indices of our input array line up to the range of possible values, doesn't it? So our range of possible values, if you remember, is between 1 and n, right? So excluding 0, and we know the length of the input is n plus 1, which is why these 4 elements represent the range of possible values, right? So we're going to make a linked list out of this. And for each node, the value of the node is going to be the number here in the index. So we have the number 0, and then the array element here is going to be the next. What is this node pointing to? So in this case, our number 0 is pointing to the node for 3, which is this thing here. And the node 3 is pointing to the node 4. Let me make this smaller. And then the node 4 points to the node 2. And the node 2 points to the node 3, which we already have. Okay, right. So we represented our input array as a linked list. What's the big deal? Well, actually, we want to find which index appears more than 1 times in our input array. See, we have 2 3s. So in the linked list world, the 2 3s would both be pointing to our 3 node, right? And you can see that being reflected here as well. We got 0 pointing to 3 and the number 2 pointing to 3. Basically, we want the node that has several incoming arrows, right? Because that would mean that the node's going to be the duplicate number. And we know that if a node has multiple incoming arrows, that is basically the cycle start node, right? The first node of the cycle. So all we need is an algorithm that figures out where the cycle starts. And then we would have ourselves the duplicate element. Yes, I know it's very roundabout, but this is the only way to make this work without using any extra space. Now, one more thing that I would like to clarify is that this ended up being a linked list specifically because of the range. I've brought it up multiple times now, but this is really important. The range starts at 1, which means that there will be no elements that is going to point to our 0 here, which means that the 0 node is always going to be the head of the list, right? The first element here is always going to be the head of our linked list. If, however, the range would start at 0, then it would be possible to have another node number that would point to our 0. And if that's the case, then we don't have a guaranteed head anymore, because as we know, heads in linked lists don't have any incoming arrows. If it did, then it wouldn't be a linked list anymore, it would just be a graph. And it being a linked list gives us a good way to work with cycles. And that algorithm is called the Floyd's tortoise and hare algorithm, right? And this is the same thing as the fast and slow pointers algorithm. Now, just as a quick refresher, this algorithm is going to create a fast and slow pointer. The fast pointer is going to move 2 units per iteration, and slow is going to move 1. And the idea is that eventually fast and slow will intersect in this linked list. And if it does intersect, then this linked list has a cycle. And if it doesn't intersect, then, well, fast just eventually arrives at the null. So in this case, we found the intersection at the node 2. So hooray, we know that it's a cycle. But that doesn't give us this number here. This is the node that we want. We want to know where the cycle started. So I want you to notice an observation here. From our intersection, the start of the cycle is 1 hop away, right? And from the head of the linked list, the start of the cycle is also 1 hop away. Let's have a look at some other examples, and you might start to see a pattern. Let's say our input is 1, 3, 4, 2, 2. Let's build the linked list out of this. That would give us this list here. And then we run our fast and slow pointers. And we can see that from our head here, we have to move 1, 2, 3 hops, right? And from our intersection, well, the shortest path is indeed 1 hop. But if you keep going, you go 1, 2, and 3, we also end up at the start of the cycle. Now, this relationship is not a coincidence. The distance from the head to the intersection is always the same as the distance from the intersection to the start of the cycle. So algorithmically, that means after we run the fast and slow pointers and it gives us the node with the intersection, all we have to do is do a while loop. And each iteration, we move head once, move the intersection once, and then we move head again, move the intersection again, and then we move the head again. Keep going until they meet. And the node where they meet is our result. We return 2, and then that's the end of it. But the biggest question is, why does this work? Why does this relationship exist? Well, that's because of maths. Let's have a look. So let's think about the distance that slow and fast has to travel, right? Okay, let's start with slow. How many nodes did slow travel before it reached the intersection here? Well, that's going to be equal to the onset here. So slow traveled, what, onset? I'll call it O plus. So let's see, this is going to be O, and this is a C or cycle. And then we have this, which is the distance between the intersection and the start of the cycle. I'm going to use a different color. And I'm going to call this our X, okay? So the distance slow traveled is going to be O plus C minus X, right? And this C minus X is this distance here. And of course, it might be a bit obvious to you, but this distance plus this distance is equal to C, right? C minus X plus X gives us the whole cycle. What about the fast pointer? How many nodes did it travel? So obviously it still had to do the O in the beginning, and then it has to loop through the entire cycle once, right? Before catching up to the slow pointer. And then so it does 1 loop, and then from here, it will travel this distance again, which, as we talked about, is C minus X. So just to simplify, it's going to be O plus 2C minus X. And we know that the fast pointer moves at twice the rate of the slow pointer, right? So the distance travel should also be double, right? So I can also say that 2 slow is equal to fast. And so if I do this like algebraically, we're going to have 2O plus 2C minus 2X is equal to 0 plus 2C minus X. We can cancel out the C's here, and then we can take the X, move it to the right side. That's going to give us an X. And then we can take O, move it to the left, and that's going to give us an O. And there you go. That's the proof, where the onset is equivalent to the distance between the intersection and the start of the cycle. Honestly, I don't think I could have figured this one out. I'm going to be so real with you. But such is the nature of Neetcode. But anyways, now that we're properly convinced, all we have to do is write this up in code. So let's go do that. So first things first, I'm going to define fast and slow. They're going to start in the beginning. Wait, let me zoom in a bit. They're going to start in the beginning of our linked list. And then I'm going to create a while loop, and then we're going to increment slow by 1. So slow is going to be equal to slow.next, right? But we're not working directly with a linked list node. And remember, in this problem, slow, which is 0, is the value of the node. And the slow.next is equal to nums slow, right? This is the slow equals slow.next. And then we do the same thing with fast. Fast is equal to Well, if I do this, then I'm moving fast one node. And if I want to move fast two nodes, then I take the result of that and then I feed it back into the array. And that's going to give me the node 2 units from where we started. And then we want to keep repeating this until slow and fast meet. So if slow is equal to fast, then we want to we want to break. And then next, I'm going to define a variable called head. And then this is the part of the code where we're going to increment a head and a pointer at the intersection one at a time until they meet. I mean, I'm going to be using the slow pointer because it's already at the intersection right now. So while head is not equal to slow, I want to increment head by 1 and I want to increment slow by 1. And eventually they're going to meet and then this condition will force the loop to stop and then we just return head, which is going to be the value of the first node in the cycle. And that's pretty much the code. All right, thanks for watching. Okay, bye.